attached to a wall a piece of a spring with stiffness 1080 Newton per meter, a damper with damping constant C, which again we'll need to determine. We've got a start which has a mass equal to 30 kilograms and the force, external forcing 25 cos omega t Newton is applied to the cart. Okay, now just some initial analysis of this thing. First thing we should also always be interested in is natural frequency, undamped natural frequency, and damping ratio. Let's first write down the equation of motion. So I get a mass 30 times x double plus damping constant, which is C, times x dot, plus stiffness 1080 times x is 25 cos omega t. Now you always want to write this in standard form, and in standard form we have that the term in front of x double is equal to 1. So what we first need to do is divide everything by 30. So I get x double plus c divided by 30 times x dot plus 1080 divided by 30 times x. 36 indeed. 36 times x is equal to 25 divided by 30 times cos omega t. And 25 divided by 30 is 5/6 cos omega t. Now straight away, one word of caution here. We're later on going to use formula for A up there. But you have to remember that this formula is for a forcing equal to cos omega t. Here we have a forcing 5/6 times cos omega t. What we know is there's linearity. If you multiply your forcing by a constant, you multiply your solution by the same constant, which means that we also have to multiply A by the same constant. So we have to multiply, if you use the formula up there, we have to multiply A by 5/6. Okay, omega n is, well, this is omega n squared. So omega n is 6 radians per second. Theta is equal to this thing divided by 2, which is C divided by 60, times the square root of 1 divided by term in front of x double, which is 1, times this term, 36. Now that's to be that square root of 36 is 6. So take this 6 here, we get C divided by 360. Okay, now in the first part of the question, we take C equal to 0. So there's no damping. And we want to know for which range of values of omega you have that the resulting steady state, the amplitude is the resulting steady state response is less than 75 millimeters. One thing to say here is that actually you cannot assume that C is exactly equal to 0, because if C is exactly equal to 0, the steady state response doesn't exist. And that's because of the fact that there is no damping, so you cannot go into the steady state response. However, in practice, systems are always a little bit damped. So this is just setting C equal to 0, is just looking at a situation where damping is very, very, very light. But there's still a very little bit of damping, which allows you to still have a steady state response. For the purpose of this exercise, we'll just assume that C is equal to 0 and apply the formula up there. So we take C is equal to 0, which by this equation also gives you that theta is equal to 0.
So for previously zeta, is it 1 over 36? Is it the square root of 1 over 36? Because I thought it would be the mass times the...
Well, the mass is here, isn't it? If I look at it here. So it would be this one, C over 2. This C over 2 times the square root of 1 over this one times this one.
Which is
going to be C divided by 360, if you do it.
Oh, okay. Yeah, sorry.
If you have something of the form n x double plus C times x dot, big M, big C times x dot, plus big K times x is equal to 0. Theta is this big C over 2 times square root of 1 over mk. You can also do it here. Big M here is 1. Big C is C divided by 30. And big K is 36. And then the formula is. Okay, C is equal to 0. So theta is equal to 0. And that means that the amplitude of my steady state oscillations, well, I'm going to use that formula. However, keeping in mind the point I just made, that here I don't have cos omega t, but 5 over 6 times cos omega t. So when applying the formula up there, I still need to multiply by 5 over 6. So I have 5 divided by 6 times the square root of omega n squared minus omega squared plus 4 theta squared omega n squared plus omega squared. But theta is equal to 0. So the second term there, the 4 theta squared omega n squared times omega squared, disappears. So this is what I have. And how can I simplify this? What is the square root of a squared? Sorry?
8.
Is that true? Square root of a squared. Small a. What is the square root of small a squared? Square root is defined to be positive, always. So, what is the square root of minus 2 squared?
2. 2.
2.
Minus 2.
Minus 2.
Square root is defined to be a positive number.
But
Square root of a number is defined to be, so the square root of b is defined as the positive solution of x squared is b. That's the definition of the square root of b. So the square root of minus 2 squared is the square root of 4. And that's the positive solution of x squared is 4. The positive solution of x squared is 4 is 2. So the square root of minus 2 squared is 2, which is the modulus of minus 2. So the square root of omega n squared minus omega squared squared is the modulus of omega n squared minus omega squared. Keep it in mind, that's essential questions like this. Square root of something squared is the modulus of the something. So this is 5 divided by 6 times omega n squared minus omega squared. And we want this to be smaller than 75 millimeters. Now keep in mind, we've got our K in Newton per meter, so we also have to work with everything in meters. So rather than writing 75, we have to write 75 times 10 to the power minus 3. 75 millimeters, 75 times 10 to the power minus 3 meters. Okay, now, so this, we want to solve this inequality. What I'm first going to do, so you want to make the omega n squared minus omega squared subject. Yeah. That's the question in the notes. You want the steady state response to be less than 75 millimeters. So that's page 262 of the notes. Okay, so we want to solve for omega. Yeah. So first instance, I'm going to make this modulus subject. So I'm going to multiply everything by omega n squared minus omega squared, or rather the modulus of omega n squared minus omega squared, and divide everything by 75 times 10 to the power minus 3. So I get omega n squared, modulus of omega n squared minus omega squared, larger, because if I multiply, so modulus goes to this side, so then it's going to be larger than something. Larger than 5 divided by 6 times 75 times 10 to the power minus 3. And 5 over 6 times 75 is 5 over 4 to 50, so it's 1 over 90. We get 1,000 over 90, 100 divided by 9. Or the engineer would say 11.1111111. I would just say 100 divided by 9 for the moment. Keep your hands off these calculators as long as possible. Yep.
Shouldn't it be 6 over 5?
No, because it's omega n squared minus omega squared goes here. Yeah? And the 5 over 6 remains here, and it's still divided by 75 times 10 to the power minus 3. Yeah? Okay, so we need to solve this inequality, so the modulus omega n squared minus omega squared is larger than 100 divided by 9. first look at what you would do if you need to solve modulus of x is larger than a given number a. And the best way to see that is just to make a picture, draw a picture. So what do you want? We have modulus of x. So modulus of x is just equal to x if x is larger than 0. Just this line, y is equal to x. Modulus of x is equal to minus x when x is smaller than 0. So that is this line here. So that's the graph of the modulus of x. And then I want the modulus to be larger than a. Well, I've got this level a here. Well, here, this line is y is equal to x. So if the y coordinate is equal to a, the x coordinate is also equal to a. And here, well, this line is y is equal to minus x. So if the y coordinate is a, then the x coordinate is minus a. So this is minus a. So you see, if you want the modulus to be larger than a, you can have two situations. It's either x is larger than a, so that is one situation, x is larger than a, or, to the left here, x is smaller than minus a. So x smaller than minus a. Now here, the omega n squared minus omega squared is the x. So here you will have either omega n squared minus omega squared is larger than 100 divided by 9, or omega n squared minus omega squared is smaller than minus 100 divided by 9. Here at the top, I'm going to take the omega squared to the right hand side by adding omega squared to both sides. So there I get an omega squared on this side, or in other words, this sign is pointing towards the omega squared. So I have omega squared is smaller than, and then I get my omega n squared. I was allowed to make mistakes this time. Does anyone notice any mistake here? Because oh no, it's okay. It's okay. Sorry. I'm mistaken in thinking that I made a mistake. So omega squared is smaller than omega n squared minus 100 divided by 9. And I know that omega n squared is 36. That's 36 minus 100 divided by 9. Or omega squared is larger than, so here I take the omega squared to the right hand side, and then the thing is pointing towards the other side, so I get omega squared is larger than omega n squared, which is 36, plus 100 divided by 9, because here take the minus 100 divided by 9 other side. Now you can take out your calculator, calculate 36 minus 105.9 and take square roots. And same here, and you find that omega is smaller than 4.99 radians per second. Or omega is larger than 6.86 radians per second. Are there any questions?
And are there two answers because of the damping ratio being critical? Or, oh, sorry, no, not critical, equal to 0? Or that,
No,
is that?
because generally, and this is something I forgot to do, so I need to do it tomorrow. Generally, if theta is between 0 and half square root of 2, and you look at the plot of A versus omega, you have what is known as resonance. And typically what you will have is that plot will be something like this. So you see, if I want it to be smaller than a certain value, you will find two ranges for omega. If, if theta is equal to 0, then you will find actually, say, this is omega is omega n. Then you will see something like really an asymptote, which really goes to infinity. Because there's no damping, so you will really have a large resonance. These peaks occur for theta between 0 and half square root of 2. Theta is larger than half square root of 2, there won't be a maximum any longer. So then you will just find one range of solutions. As I said, this is something I just realized I forgot to do today, so I'll also do that tomorrow. Just look at part B, where the fun really starts. So I'll finish with that today and then obviously recap it tomorrow also, and it will be good if you would also have a look at it yourself overnight. We're now assuming that C is equal to 36 Newton second per meter. So C now is 36 Newton second per meter, and that means as C, or theta is equal to C divided by 360, that theta is equal to 0.1. And it also means that 4 times theta squared times omega n squared is 4 times 0.1 squared is 0.04 times omega n squared. Omega n squared is 36. So you got 0.04 times 36, which obviously is equal to 1.44. So 4 theta squared times omega n squared is 1.44. And that now gives that your A. So for A, I'm again going to use that formula. Again, keeping in mind that because of this, I still need to multiply by 5 over 6. So I get A is 5 over 6 times the square root of omega n squared, which is 36, minus omega f squared, times 4 theta squared omega n squared, which is 1.44, plus 1.44 times omega squared. And that again now needs to be smaller than 75 times 10 to the power minus 3. Okay, for time's sake, I'm now going to take a quick step, which you, well, just, I'm going to do it a bit more slowly tomorrow. This is the same as saying that square root, I'm going to save myself some writing, so the square root there of all this rubbish has to be smaller than 5 over, has to be larger than 5 divided by 6 times 75 times 10 to the power minus 3. And, well, we've just seen that that is equal to 10, or 100 divided by 9.
Should the inequality be switched around?
Yes. Thank you. Larger. And the square root goes to the other side. Okay, now, next step is square everything. So, if I square the square root, I get 36 minus omega squared. Squared plus 1.44 omega squared has to be larger than 100 divided by 9 squared. And what I'm now going to do is expand everything. And keep in mind that I have an omega square here, and if I expand it, I get an omega to the power 4, which would mean you need to solve an inequality with a polynomial of degree 4. But do keep in mind that everything depends on omega squared. So you can make omega squared the subject rather than omega itself. So if I expand, I get minus omega squared plus omega to the power 4. But I rather write this omega squared, just to indicate that omega squared is going to be the subject. Then I get minus 2 times 36 omega squared plus 1.44 omega squared. So it's minus 72 plus 1.44, that's minus 70.56 omega squared. Then plus 36 squared. Then take this 100 divided by 9 squared to the left hand side. So that becomes minus 100 divided by 9 squared has to be larger than 0.
So, is that all squared or 109 squared only?
Sorry?
Is that all squared or 109 squared only?
Thank you. Square that. It's getting late. Okay, now, so I have something of the form x squared minus 70.56 x plus constant 36 squared minus 100 divided by 9 squared is larger than 0. You want to solve this for x. Let's just draw a graph of this x squared minus 70.56 plus the constant is equal, not just a graph of that thing. When x is 0, it's equal to 36 squared minus 100 divided by 9 squared. And if you calculate that, at least you find something that's larger than 0. Because 100 divided by 9 is smaller than 36. So it starts larger than 0. And what it will do is, it does something like this. So it is larger than 0 when x is smaller than this value, and x is larger than that value. And how do you find these two values? Well, you find it by setting this thing equal to 0, i.e. applying the quadratic formula to this thing. So if you apply the quadratic formula, you find two solutions. And then the conclusion is that omega square is either smaller than this value, or omega square is larger than this value. I'll go through that in a bit more detail tomorrow. Do try this at home, because you might also be asked to do this in an exam, or this, or something similar. Here in this case, you should find that omega is smaller than 5.18 radians per second, or omega is larger than 6.61 radians per second. Are there any questions? Okay, so I didn't keep my promise to finish today, so see you again tomorrow.